So a function is a correspondence between elements in a first set called the domain and elements in the second set called the range, such that each member of the domain corresponds to, and this is important, exactly one member of the range. Now here is a representation of a function as a diagram. We see the elements in the first set here, set X. So this one here are our domain. And the second set, Y, is the range. Now we see that each element in set X corresponds to exactly one element in set Y. So you see here that 1 corresponds to D, 2 corresponds to B, 3 corresponds to C, and 4 corresponds to A. So this is a function. So we see the correspondence there being represented by the arrow. Now, we can also regard a function as a set of ordered pairs, which is something that we're probably a little bit more familiar, especially when we consider graphs, like, oh, if we have an x value, there's associated y value, right? However, if you're thinking about functions as ordered pairs, you gotta make sure that no two pairs have the same first coordinate paired with a different second coordinate, because at that point, then you're saying that one input has two different outputs, and that's a problem. That's not a function. So here we have a representation of a function as ordered pairs. So we have f is equals to the first order pair 1, 9, then the second order pair 4, 6, third ordered pair 3, 25, and fourth order pair 5, 9. Now in this example, what is the domain and what is the range? Now remember, the domain is the elements in the first set. Now you can also think about them as inputs, which we'll talk about shortly. So in this case, the domain for this function are the x values, the inputs. So it'd be 1, 4, 3, and 5. So 1, 4, 3, and 5. Now what about the range? The outputs. So the range would be the y values, the 9, the 6, the 25, and the 9. So we have 9, 6, 25. Let me move this a little bit more here. I'll just put it here on the side. There we go. The range is 9, 6, 25. Now there is another 9 here. However, when we are writing the elements in one set, guys, we don't really need to repeat them, because when we're saying that there is an element in the set, we're saying that that number is there, and we don't care about how many times it might be in the set. All that we're doing is we're saying that, hey, that number is in the set, so there is no need to repeat them. The range would have the numbers 9, 6, and 25. Okay, so now let's take a look at some examples. Let's see if we can determine whether or not each correspondence is a function, and if it is a function, let's go ahead and find the domain and the range. And let's take a look at examples A and C. So for example A, we're given the input, the cities, and the output, the population in thousands. So let's see, is it a function? Well, the city of Lubbock has a population of 206,000, Colorado Springs has a population of 307,000, Omaha has 404,000, Yonkers has 197,000, and Sacramento has 445,000. Now, is this one a function? Well, I do see that each of my inputs, the cities, have exactly one output, one population. So this one here is a function. One input gives us one output. So it is a function. Now, in order to find the domain, it's a lot of cities to write, so for the domain, I'll just write down the cities. There we go. And for the range, I'll just put in the populations. Okay, great. Well, I'll just clarify one more thing here. It is a function because one input gave us one output. There we go. All right, so now let's take a look at example C here. So for example C, it looks like we're given the the function defined here as a set of ordered pairs. So let's take a look. For the first ordered pair, we have 2, 3, then 2, 4, 0, -1, and 3, -1. So it looks like there's a couple of repeating values both for the input and for the output. Is that a problem? Well, let's see. Now, if you can't identify right now whether it's a function or not, what I always like to do is essentially write it as a diagram. So I'll just put here the domain on, or the inputs as the first set. So we'll have here the 2. There's another 2, but remember we only write it once. And 0 and 3. So 2, 0, and 3. So here are the elements in our first set, the domain, the inputs. Now let's do the range. So for the range, we'll have the y values, the outputs 3, 4, -1, and again there's another -1, so we only write it once. So 3, 4, and a -1. Okay, so we get to see that the 2 corresponded with the 3. The 2 also corresponded with the 4. The 0 corresponded to the -1. And the 3 also corresponded to the -1. Okay, now, is this a problem here? Is this a function or not? Well, take a look at the entry or the input of 2. The 2 has 2 outputs. And at that point, remember, one input can only have one output, so the 2 is a problem, so it's not a function. Again, because the 2 has 2 outputs. Okay, now what about the fact that the 0 and the 3 both have an output of -1? Is that a problem? Not really, because notice the input of 0 has one output. It happens to be -1, that's fine. And the 3 also has only one output. The fact that they both have the same output, it's not a problem. They're still a function. The only problem is one input has 2 outputs. Okay, so now let's talk about the function notation and see how we can evaluate function. The notation y equals to f of x is called function notation, where the input is x, the output is the y value, and the name of the function is f. So here we have y equals to f of x. So whatever's inside the parentheses here, this one here is your input, the number or variable you're putting into the function, sometimes another function. The y here is our output, and the f here is simply the name of the function. Now, the most common letters used to denote functions are F, G, and H, but I mean, you could use any letter really. Those are just the most common. The variable x, aka the input, is the independent variable, and the variable y, aka the output, is the dependent variable. And if you think about it, it makes sense because we're putting in one x value and we're seeing what y value do you get after you put in that x value. So let's take a look at a couple of examples here with the function notation. So we have the following. We're given the function f of x equals to x squared minus 3x, and we want to find the following. And again, we're only going to be taking a look at 2 examples. I'm thinking of probably taking a look at example 2. Actually, let's take a look at example 1. This is a nice warm-up. Example 2 and example 4. Now, in order to evaluate a function, you can think of the function as kind of like a formula or a rule that tells you what to do with any input. So for example, the function that we're given here, f of x is equals to x squared minus 3x. Well, that x here, our input, is really not important. It could be any number, but the function, the formula, is telling us to do the following. We'll take the function value of some input, whatever we choose, well, not exactly whatever we choose, whatever we're told in this case, is going to be equals to, again, the x is not important, it's just whatever the input is. The rule tells us that we take the input, we square it, and then we take away 3 times the input. Oops. There we go. Okay, so let's evaluate f of 4. So we have f of 4 here. F of 4. And there we go. This 4 here is our input. So we already know what the rule is, or what the function is telling us to do with the input. We take the input, we square it, and then we take away 3 times the input. So we have 4 squared minus 3 times 4. And that's going to give us here a 16 minus 12, which is equals to 4. And there we go. It just so happens to be that when the input is 4, the output for the function is also 4. Now again, this was just a coincidence. If I plug in 2, I would have gotten a different output. Alright, so let's take a look at the next example where they're switching things up a bit, because now you have f of a. So what is f of a? The math is no different. The input is a. So we already know what the function tells us to do with the input. We take the input, square it, and then take away 3 times the input. So we should have here an a squared minus 3a, which is just going to give us an a squared minus 3a. And there we go. Not much else that we can do. I mean, maybe factor out an a, but leaving it like that is perfectly fine. Okay? Alrighty. So now let's take a look at the more complicated example. And it's good because there's a calculus class after all. So let's take a look at the following. What is f of x plus h minus f of x all over h? Now it might seem a little bit daunting at first because, well, it looks like on the numerator for our expression we have f of x plus h minus f of x, but for now, guys, remember the math is still the same. So let's first focus on f of x plus h, which is basically what we have here in example 3, so I'll just do it over here. What is f of x plus h? Well, what is the input? The input is always whatever's inside the parentheses here. So here's the input, x plus h, and we already know what the function was doing to the input. It was squaring it and then taking away 3 times that input. So we'll have here f of x plus h, so that's going to be equals to x plus h squared minus 3 times the input, the x plus h. Okay, so now let's simplify it here. Now, very important, guys, we are squaring. Does that mean that we take the second power and apply it directly to the x and the h? Not quite, because remember, whenever we're squaring something, we're being asked to multiply that thing by itself. So that's why I would give you, let's say I give you a 4 squared and I ask you what that was, well, then you might be inclined to say 16, because 4 squared is 4 times 4, which is 16. So that's exactly what we're going to be doing here. We're going to be squaring the x plus h. So let's see, x plus h squared is x plus h multiplied times itself. So now, since we're multiplying a binomial by itself, you get to see here that, oh yeah, it looks like we are foiling. We do an x times x, then an x times h times x, and h times h. So that should give us here x times x is x squared. I'll do it here. It's going to be an x squared plus an h, or an x times h, which is an hx, plus another h times x, that's an hx, plus an h squared. And we get to see here that we do have some like terms. So we'll have here x squared plus, we have 2hx plus h squared. And there we go. We figure out what is f of x plus h. F of x plus h is x squared plus 2hx plus h squared. Okay, so now let's go back to example 4, since we already know this part. But now let's put everything together here. We have the f of x plus h, which I'll copy it again here in light blue. So we have x squared plus 2hx. Oops, well, my bad, guys. Because we were doing, we only did the x plus h squared, but we also need to subtract the 3 times x plus h. So that's going to be here a minus 3x minus 3h. There we go. Alrighty, so let's just copy all that. X squared plus 2hx plus h squared minus 3x minus 3h. Okay. Now we're also being asked to subtract f of x, so minus f of x. Now, at this point, there's no need to plug anything in because we already know what f of x was, right? F of x was x squared minus 3x. So I'll just put it here in, I'll put it in orange. Minus x squared minus 3x. Now we gotta be really careful here because we're subtracting the f of x, so we're subtracting the whole thing. Anytime that we do this type of operations when we're subtracting more than one term, it's always good to include parentheses. In fact, it's not good, it is like required, otherwise you might be missing a negative, or you might be making some mistakes with negatives so we don't include the parentheses. And this whole thing was divided by the h. Okay, so let's simplify it a little bit here. I'm gonna go ahead and distribute the negative. So let's see, distribute the negatives, and let's rewrite everything here. Okay, so there we go. Now let's continue to simplify it a little bit more, because the nice thing about this type of problems, there's actually some nice things about this problems, guys, it could be worse, is that a lot of things will cancel, and namely the terms without the h. So we get to see here that I do have an x squared, but I'm also subtracting an x squared. I'm taking away a 3x, but I'm also adding a 3x, so all of it cancels. And we're left with a 2hx plus h squared minus 3h. And I think that's everything that I see on the top. The whole thing is being divided by an h. Now pay attention here though, because it looks like I have an h. Put in a different color here. Let's go with green. I haven't used green. So we have an h here, we have an h squared here, and we have another h here. So it looks like I can factor out an h from everything on the top. So I'll take out an h, and we're left with a 2x plus h minus 3. And the whole thing was being divided by an h. And lo and behold, guys, we have an h on the top and h on the bottom. They can cancel, so our last and final answer is 2x plus h minus 3. There we go. Much cleaner. Perfect. Okay. Now, one more thing I want to mention here is that even though this process might have been quite a bit long, this expression is actually one of the cornerstones of calculus, so it's good to see it early and get a little bit familiar with it, because later on it's going to lead into many different type of applications. Okay, alrighty, so this is it for this video. We're going to move on to